Hey everyone, this is a relative acceleration example, and it's simply a continuation of our instantaneous center of zero velocity question, where our velocity at b was negative 1.155 j meters a second, and our angular velocity omega was 0.770 k radians a second, so 0.770 radians a second counterclockwise. The question simply states that the end A of bar AB is sliding horizontally to the right. Determine the acceleration of end B for theta equals 30 degrees, where the velocity and acceleration of point A are 2 meters a second and 1.2 meters a second respectively, both to the right. Now the first thing we're going to do is declare all our, well not declare, but we're going to write down all our variables so that we can go back and solve the question much easier when we know all of these terms. So our velocity of A, I don't think it's really necessary to know the velocity of A. We can just say V of A is equal to 2I meters second. Now A of A, this is a bit more important. The A of A term is 1.2I meters per second squared. We can then go ahead and write our relative acceleration equation like so in terms of the acceleration of A, which is the general way to do it. Now we note that the acceleration of B with respect to A is negative of this vector, or the negative of this vector. So if we add the negative of this vector to both sides, then we end up getting our acceleration of B, which is what we're looking for in the question statement. So acceleration of B is equal to the acceleration of A minus the acceleration of A with respect to B. We can then write our relative acceleration in terms of alphas and omegas, because it represents rotation. So our acceleration of A with respect to B is equal to alpha cross R A with respect to B plus omega cross R of A with respect to B. Now, seeing as we already know that our omega is 0.770 k radians a second and our alpha term is unknown, the first thing I think we should do is write our alpha in terms of what it will be. So it's a positive rotation, so a counterclockwise rotation, so alpha k. And we don't know that yet, but we do know that it's in the k direction, because rotation in 2 dimensions is always out or into the page. And if we look back at this diagram here, we can see our relative position, which is our R of A with respect to B, is the vector position from B to A. So this plus this, so this J plus this I, which is negative L cosine theta Rj plus L sine theta I. So our R of A with respect to B in components is negative L cosine theta j plus L sine theta I. If we go ahead and substitute in the values, so 3 meters as given in the question, bar is 3 meters long, and our theta equals 30 degrees, we substitute that in, we'll get a value for our relative position. So that equals negative 3 cosine 30 degrees j plus 3 sine 30 degrees I. Okay, now we've got our relative position, we can substitute that back into our relative acceleration equation and then solve for A of B. Now the first thing to note that the A of B, so A of B is equal to the magnitude of A, or A of B, in the j direction, because there's only acceleration downwards. almost run out of paper on this. So acceleration of b is the acceleration of b in the j direction, or the magnitude of the acceleration of b in the j direction. So what we can do is solve for our acceleration of b and then equate coefficients like we have done in other questions, or like we will do in future questions as well. So that's equal to 1.2 I, because that's our acceleration of a, minus our alpha k cross our r, which was 3 sine 30 degrees I minus 3 cosine 30 degrees j. So that's our alpha cross r term. And our omega cross r term is this, 0.770k cross 0.770k cross our r. So 3 sine 30 degrees I minus 3 cosine 30 degrees j. Okay, so the next thing we have to do is solve this term in here, and then we're going to solve our alpha cross r term simultaneously. So this is our omega cross r term here. That's what that term is there. So what we might want to do is move these out of the way. I'll keep this page, or the end of this page here. And we can then go ahead and say that this is equal to 1.2 I minus 1.5 alpha j minus 2.598 alpha I, and we're going to subtract our 0.770k cross negative 1.155 j plus 2.001 I, and that ends up giving us 1.2 plus 0.889, and we're going to subtract our 2.598 alpha term, and that's our I components of acceleration. And we're going to add the j components, and the j components end up being our 1.5. So we're subtracting 1.5 alpha plus 1.540 in the j direction. Now, if you have a look at our acceleration of b, that's only in terms of j. So this acceleration in the I direction must be 0 on the left hand side. So the sum of these terms is going to be 0. So in the I direction, and in the j direction it's going to be A of B, obviously, if we're looking at magnitudes. But I'm going to cover that in the next video. I'm going to run out of time in this one. Thanks for watching.